Now, let's jump into the third section about the watermark mechanism for flink.
Here, let's just have a review of the out-of-order issue. In short, those events that happened earlier may be ingested and processed later, as is shown in the figure below. And by the way, this issue is indeed a very common situation in actual cases. Therefore, to resolve the out-of-order issue, we need the watermark. Indeed, watermark is just a symbol or a notation to notify the processor that after a certain time period, delayed messages should no longer be received. Let's have a look at this example, and it might provide you a better understanding of the watermark. Please remember, a watermark is just a timestamp which suggests a particular time point, and watermark T, or WT in short, indicates that all data whose timestamp is less than or equal to T has arrived and will not be received in the future. In this graph, W11 refers to the timestamp of event 11, which means event 1 to 10 has arrived successfully. If one of the 10 events is late, for example, event 9, then event 9 will not be received by watermark. This is how watermark works. And clearly, watermark is only for the out-of-order situation. For the ordered streams, watermark is unnecessary because the order is perfect. And in actual cases, Flink defines the watermark via the maximum time delay. For example, in the figure below, we set a maximum time delay as 2 seconds. And the watermark is used together with a tumbling window whose window length is 6 seconds. Then, after 6 seconds, the latest event has a timestamp of 7. So the watermark is now 5, according to the 2-second time delay we set before. Okay, similarly, the second window ends on event 12, and now the watermark is 10 as a result. And by observation, before watermark 5, the event 1 to 5 do arrive in the first window, so the processor can destroy the first tumbling window safely. However, from the method introduced before, you might find that the watermark is not 100% accurate in some cases, right? That is because in the real world, we cannot obtain a perfect watermark value. So we tend to use the approximate watermark T as introduced. By doing so, there is still a low probability that the data before timestamp T will be received even we set up a watermark. And we define those data as the delayed data. And then we define the maximum latency through the .allowed lateness time step. The latency is 0 by default, which means we do not allow any lateness, but we can make configuration depends on the real cases. But how do we deal with the delayed data? There are also 3 methods. The first method is to reactivate the closed windows and recalculate to correct the results. In this method, the previous window is not destroyed, but preserved for a certain time period. And if the delayed data arrives within the time period, they can be added into the previous window. By contrast, the second method is to set up a new window and calculate the delayed data in the new window separately from the previous one. The last method is to consider delayed events as an arrow and discard them directly. So the third method requires the least resources, but by doing so, the result may not be accurate. So actually, we seldom use the third method in real cases. And as for the first 2 methods, they have their own names here. So the side output refers to the second method, while allowed lateness refers to the first one. Both methods are applicable in real cases, but please note that for the allowed lateness should not be too long, and the delayed events should not be too many. Otherwise, it will cost too many resources to preserve the previous windows.
Okay, that's all for the watermark mechanism for Flink. And we say watermark is nothing but just a timestamp itself. Now, it's time for us to jump into the last section of Flink, which is about the fault tolerance of Flink.